Hi. All right, so we are going to be talking about waves today. This is chapter 19 if you're using the big book. If you're using the condensed book that is 3-hole punched and you put into the binder, it's chapter 9. So we're going to talk all about waves, wave motion, how waves move through space. So to begin with, we'll define a wave. So we start by talking about vibration. So a vibration is a periodic wiggle in time, meaning it keeps happening. So as it keeps happening, it moves along. And as it's moving, it is a wave. So a periodic wiggle in both space and time is a wave. A wave goes from one place to another. Some examples that you are familiar with are light. Light is an electromagnetic wave that needs no medium. So we'll talk about what that means a little bit today as we go on, no medium. Sound is a mechanical wave. It does need a medium. All right. So a wave is like an extended vibration. It's moving along through space. So here at the beginning of our discussion, I'd like you to picture a pendulum. So it's like that thing that hypnotists hold that goes back and forth, right? So if you took something heavy like a stone and put it at the end of a piece of string, what you have then is a pendulum. The pendulum goes back and forth regularly at a rate that depends only on the length of the string part of the thing. It does not depend on how heavy that stone at the bottom is. Just as we saw in earlier chapters, that the mass does not affect the rate at which something falls to the ground. So you can remember when we had that sheet of paper and an identical sheet of paper, and I crumpled one and we left one uncrumpled. They both had the same mass, but you saw that's not what affected how far they fall or how quickly they fall. So it doesn't matter how heavy that thing at the end of your string is. All that matters is how long the string is. So the time that it takes for the thing to go back and forth is called the period. So if I have my pendulum, I'm holding it, and I draw it to one side, and I'm holding it, it's there before I let it go, and then I let it go, it starts to swing. So it's here, it's hanging straight down, and then it goes all the way to the other side, and then it comes back. When it ends its journey, that took one period. So the longer the length of the pendulum, the longer that period. And so you'll remember that this is the length of the string. So that's L. So let's say you have a 1 meter long pendulum. It has the bob is what we call the thing at the end of it, the stone. So it has a stone that has mass of 1 kilogram. So now you get rid of that 1 kilogram mass and you put on a different mass, it's 2 kilograms. How does the period of the pendulum change? How will the period of the pendulum change? So I'm going to ask you, what does the period depend on? And remember that period is an amount of time. So what does the period depend on? How heavy the stone is, how long the string is, how you're feeling that day. Mass change, that doesn't affect the period. It only depends on the length of string. Mass changed doesn't affect how long it takes. So it will remain the same. We did not change the length of string. So now say you have a 1 meter long pendulum and it has a bob with a mass of 1 kilogram. And now you take that bob, that weight at the end, and you tie it to a different string. The length of the pendulum is now 2 meters. So the length increased is what happened here. Length increased. Well, we just talked about the period being dependent on the length. The longer the length, the longer the time it takes to swing back and forth, which is what a period is, the time it takes to get all the way back to the beginning. So I want you to remember that period is the time it takes to get back to where it started. Time to complete one cycle. Back and forth. So it's longer. So hopefully you have realized that the period will also increase. The length increase, the period will increase. The longer it is, the longer it's going to take it to go back and forth. And remember, that's one period, how long it takes to go through one cycle. So now let's talk more about what you think about, that shape you think about when you think of a wave. A wave is represented by a sine curve. Don't get freaked out by that. I'm not going to ask you to do a lot of trigonometry or anything like that, but that's what that shape is that we call a wave, that up and down shape. So if I draw this, I am drawing a sine curve, and hopefully it looks, I'm trying really hard to be neat, so hopefully it looks pretty regular there. So you can get that if you were to trace out the path of a swinging pendulum over time. So I want you to picture this. Say that I have this pendulum, just like is in the picture here. If you're looking at the picture, this is the bob of the pendulum, and say that I filled it with sand and it had a little hole, or you could picture, you see there's that paper underneath it, you could picture that I just put ink, like really wet ink, right on the tip of that thing, and it's just barely touching the paper, like not enough to affect its movement, but it's touching the paper. So that paper is going to be moving along at a certain rate underneath it. So we can picture like it's on rollers, right? So the paper is coming out and it's moving this way, and we'll say it's moving nice and regularly. You can picture it moving nice and slowly. So this is the paper. I really wish I had better art skills at this point. Okay, so that's the paper. It's moving along. And then above the paper, you've got this thing, right? And it's swinging this way, sorry about that, and that way. So the pendulum is swinging like to the left side of the paper, to the right side of the paper, left side of the paper, right side of the paper. So if the paper is moving, you can see it's going to make that nice up and down shape, and you can see that's the shape that's getting made here. So the pendulum is going like this, back and forth like this, and the paper is moving in this direction. So the paper is moving like this, the pendulum is moving like this. And you get that nice sine curve shape on the paper. We'll talk about all this stuff. Hold on. All right. So if you're looking here, you can see that nice wave shape that we've been talking about. So kind of picture this as the pendulum, this thing here that you can see it's on the spring. So this would be like the bob. So picture it has a pen on that underside there, a little bit of ink or something, and it's going back and forth like this. It's going up and back in the same spot, but the paper is moving, okay? So as it goes up and down, that sine curve will get traced out, and you can see this wave shape. So let's talk about that. How far up it is from the middle point there, this middle point, the maximum distance it goes up, you can see happens right there. We call that the amplitude of this wave. And we're starting not at like what you would call the bottom, but here at this midpoint. And you can see it goes down that exact same distance when it goes down to its lowest point. So the amplitude and is not only the distance from that middle up to its highest point, but it's going to be the same distance from that middle down to its lowest point. And then the wave length is going to be from the absolute peak to the next absolute peak that happens, not from peak to bottom point, but from peak to peak. This is getting kind of messy. All right, so the wave length is going to be from here to here. That's going to be the wavelength, the length of this wave. That is one whole cycle of the wave. It took that pendulum, whatever its period is, to go through one cycle from there to there. And you need to know that this is the Greek letter lambda. You're learning a lot of Greek in this class. This is the Greek letter lambda, and we use it all the time to mean wavelength. So when you see lambda, you're like, oh, I know what you're talking about. You're talking about the wavelength. So lambda. It looks kind of like an upside down Y a little bit. All right. So we call these high points on the wave, amplitude up from that midpoint, we call those the crest. The low points on the wave, we call those the troughs. Crests and troughs, again, we went through this just a second ago, but crests and troughs are the same distance from that midline. All right. So the amplitude is the distance from the midline up to the top, or the distance from the midline down to the bottom. And the wavelength is the distance from the top of one crest, like right there, it's the very highest point, to the next identical point, the top of the next crest. So actually, we define the wavelength as any successive identical part of the wave, but I think right now the easiest thing for you to think of is to just think crest to crest for wavelength. But say here I'm at 0, right? If here I'm at 0, you can say, oh, well, here I'm at 0, but look, what is the difference? Here I'm at 0 on my way down, and then I go down, I come back up, I'm at 0. I'm at 0 on my way up, just like I was here. Now I'm at 0 on my way up again. So that is also going to be that same distance, a wavelength. But I think probably for the sake of simplicity, it's easiest to just think of peak of crest to peak of crest for wavelength. So how frequently that vibration occurs is called the frequency. The unit that we use for frequency is the Hertz, and our abbreviation is Hz. It's named after Heinrich Hertz. I think he might have been some kind of radio engineer. So if I have a frequency of 1 Hertz, that means I am making 1 vibration each and every second. Things that we've been talking about, like objects that you can see and hold, like that pendulum, would have a frequency of a few hertz, meaning it would be going back and forth a few times every second. So hertz means cycle per cycles per second. Cycles per second. Oh, the eraser, sorry about that. Cycles per second. And that's our hertz. Sound waves, you probably maybe heard this term hertz before. Sound waves have frequencies from a few hundred up to a few thousand hertz. Radio waves have frequencies of a few million hertz. You don't hear radio waves, you hear what your equipment, how it receives and responds to radio waves. Cell phones operate at a few billion hertz or gigahertz. You might remember that prefix, that capital G means giga. So I would say gigahertz there. And that prefix large M is mega, so that would be megahertz. You don't really need to know that, but we're all scientists, right? And it can't hurt you to get some more practice with the metric system. Frequency is talking about the number of back and forth cycles in a given time. So the number of waves passing any point per second. So for example, if I had 2 vibrations every 1 second, that would be a frequency of 2 vibrations per second, or 2 hertz. I've drawn these pictures here to help us try to understand a little better. So I want you to picture you're that green guy, you're the observer, and this is a wave coming at you. If you want to think of it as a sound wave, that's fine. But let's just say they're both moving at the same speed. They're moving this way, they're coming past you. If it's a sound wave, you're hearing the pressure that it's making is how you're experiencing that sound wave. We'll talk about that later. But this wave is moving this way, right? So how many of these peaks are hitting you every second, right? So let's say the distance from here to here is 10 meters, and this wave is moving at 10 meters per second. Well, this would hit you, and then, well, let's just say the whole wavelength is 10 meters. Let's fix that. Here to here. And we're going to use that lambda. Let's get some practice with lambda. So I'm going to say the whole wavelength is 10 meters, and the wave is moving at 10 meters per second. So that, this first one hits you, and then a second later, the next one hits you. So that's just 1 hertz. You wouldn't even hear that. That's too low. But let's say this one's going to be too low too, but it'll still work. So that's not what I want. Let's say from here to here is the equivalent distance. Now this is a wavelength now. You can see the wavelength is much shorter. But let's say that this whole thing is 10 meters, and this wave is also moving at 10 meters per second. How many of those peaks are going to hit me in 1 second now? Well, let's see. I have 1 second later, this will hit me. Or no, this will hit me, and then 1, 2, 3, 4, 5. So that's going to be 5 hertz. In 1 second, I will get 5 of those peaks. 1, 2, 3, 4, 5, 6. 6 of those peaks, sorry. Actually, in 1 second here, you would get 2 of those. You get this one and this one in that 1 second. So the second one is higher frequency. Those peaks are closer together. So both waves are moving at the same speed. Both waves are moving at the same speed. The bottom wave is higher frequency. Because more of those peaks are going to pass the same point every place. It's going to go through more wavelengths. Bottom wave has higher frequency. All right. So the period we've talked about, that's the time it takes to complete one vibration or one cycle. You can think of it as the time to go one cycle. The period is related to the frequency by this inverse relationship. So the period is 1 over the frequency. The frequency, same deal, is 1 over the period. So if you know the frequency, you know the period. If you know the period, you know the frequency. So the period is the time it takes to complete one cycle, and usually that's given in seconds, fractions of a second a lot of times. And the frequency is cycles per second. So a pendulum that makes 2 vibrations in 1 second has a frequency of 2 hertz because it completes 2 cycles every second. The period is 1/2 a second because it takes 1/2 of a second for it to complete 1 whole cycle. All right, so say we have a sound wave with a frequency of 500 hertz. I want you to stop right there. Think about, what does that mean? That means it is completing how many cycles every second? Hopefully you all said 500. So if it has a frequency of 500 hertz, it's completing 500 cycles in every second. So if you're the little green guy standing there, 500 of those peaks are going to hit you every second. So what I want to know from this frequency of 500 hertz is, what is the period of the sound wave? So period is 1 over frequency. It's related. So if we know one, we can figure out the other. So 1 over 500 cycles per second. So that's going to give me a period of 0.002. You can do this on your calculator, yeah? 0.002 seconds. So that's how long it takes to complete one cycle. Time to complete one cycle. All right. That's right there. Hey, look at us. We got the right answer. Good work, guys. Awesome. You guys are awesome. All right. Let's say I have a wave and its frequency is 20 hertz. I want to know its period. Well, we learned this. We learned that the period is 1 over the frequency. So the period is going to be 1 over 20. So 1/20th of a second, right? So my frequency is 20 hertz, so that means I complete 20 cycles every second. Therefore, my frequency, or my period, is 1/20th of a second. That's how long it takes me to complete one whole cycle. All right. let's talk a little bit now about how waves move. Let's save that for the next one. So what we talked about mainly in this section, and what I hope you're going to come away knowing, is you'll have a definition of wavelength. You can, as we start talking about waves, it's probably going to be easiest to think of going from peak to peak, crest to crest, and that is a measurement of length. So we'll talk about it in meters, centimeters, micrometers, nanometers, something meter with some kind of prefix, okay? Amplitude is also a measurement of length. So again, centimeters, millimeters, something like that. And that's midline to either the crest peak, the highest point, or midline to the trough bottom, the lowest point. Frequency is how many cycles that wave completes per second. So remember the little guy, how many peaks are hitting you every second? It's going to depend on how fast that wave is traveling, but also how it's shaped, how close those peaks are. And that is a measure of cycles per second. So our unit that we have in there is time. And it's a rate, frequency is a rate. And period is how many seconds it takes to complete a cycle. So we're talking about a measurement of time there. So it's how long it takes for the wave to go through one whole cycle.